Welcome to a fascinating exploration of quantum physics, where we'll venture into the mysterious realm of the incredibly small and discover how reality itself behaves in ways that challenge everything we thought we knew about the universe. This journey will take us through the fundamental principles, strange phenomena, and mind-bending implications of quantum mechanics, the science that governs the behavior of matter and energy at the smallest scales imaginable. At the heart of our everyday experience, the world seems solid, predictable, and continuous. Objects have definite positions. They move along clear paths, and cause and effect follow logical sequences. But when we zoom in to examine the building blocks of reality itself, the atoms and subatomic particles that make up everything around us, we find ourselves in a realm where the rules completely change. This is the quantum world, a place where particles can be in multiple places at once, where observation changes reality, and where the very notion of certainty dissolves into clouds of probability. The story of quantum physics begins in the early 20th century, when scientists started noticing phenomena that classical physics simply couldn't explain. For centuries, physics had been built on the elegant equations of Isaac Newton and James Clerk Maxwell, theories that described motion, gravity, light, and electromagnetism with remarkable precision. These classical theories worked beautifully for describing planets, projectiles, and everyday objects. But when scientists began probing the atomic realm, they encountered behaviors that defied all classical expectations. One of the first hints that something strange was happening at small scales came from the study of blackbody radiation. When objects are heated, they emit electromagnetic radiation, and the spectrum of this radiation depends on the temperature. Classical physics predicted that heated objects should emit infinite amounts of energy at short wavelengths, a prediction so absurd it was called the ultraviolet catastrophe. In 1900, a German physicist named Max Planck solved this problem by making a revolutionary proposal. He suggested that energy isn't continuous but comes in discrete packets, which he called quanta. The energy of each quantum is proportional to the frequency of the radiation, with the constant of proportionality now known as Planck's constant. Planck's constant, represented by the letter h, has a value of approximately 6.626 times 10 to the negative 34 joule seconds. This incredibly tiny number sets the scale for quantum effects. When you multiply h by the frequency of a photon, you get its energy. This relationship, energy equals h times frequency, was the first equation of quantum mechanics, and it introduced the concept of quantization that would revolutionize physics. Building on Planck's work, Albert Einstein made another groundbreaking contribution in 1905 when he explained the photoelectric effect. When light shines on certain metals, it can knock electrons loose from their surface. Classical wave theory predicted that brighter light of any color should eventually provide enough energy to free electrons, but experiments showed something different. Only light above a certain frequency could eject electrons, regardless of intensity, and the energy of the ejected electrons depended on the light's frequency, not its brightness. Einstein explained this by proposing that light itself comes in quantum packets, later called photons. Each photon carries energy equal to Planck's constant times its frequency, and an electron can only be freed if a single photon has enough energy to overcome the binding force holding it to the metal. This particle-like behavior of light was puzzling, because numerous experiments had demonstrated that light behaves as a wave, creating interference patterns and diffracting around obstacles. How could light be both a wave and a particle? This question would lead to one of the most profound insights in quantum physics, the concept of wave-particle duality. In 1923, a French physicist named Louis de Broglie made a bold proposal. If light, which everyone thought was a wave, could behave like particles, perhaps particles, which everyone thought were solid objects, could behave like waves. He suggested that every particle has an associated wavelength, given by Planck's constant divided by the particle's momentum. For everyday objects, this wavelength is so incredibly small that wave effects are undetectable. But for tiny particles like electrons, the wavelength becomes significant and can produce observable interference effects. De Broglie's hypothesis was confirmed just a few years later when experiments showed that beams of electrons could indeed create interference patterns, just like waves of light. When electrons are fired one at a time at a barrier with two slits, they don't simply pass through one slit or the other as particles should. Instead, they create an interference pattern on a detector screen. with alternating bands of high and low electron arrival probability. This pattern can only be explained if each electron somehow passes through both slits simultaneously as a wave, interfering with itself before arriving at the detector. The double-slit experiment with electrons revealed something truly bizarre about quantum reality. If we try to determine which slit an electron passes through by placing a detector at the slits, the interference pattern disappears, and the electrons behave like ordinary particles, passing through one slit or the other. The act of observation fundamentally changes the outcome of the experiment. This isn't a matter of clumsy measurement disturbing the system. It's a fundamental feature of quantum mechanics. The electron doesn't have a definite path until it's observed. Before measurement, it exists in a superposition of states, simultaneously taking all possible paths from source to detector. This leads us to one of the most important concepts in quantum mechanics, the principle of superposition. In classical physics, an object is always in one definite state. A coin is either heads or tails. A light switch is either on or off. But in quantum physics, systems can exist in superpositions, combinations of multiple states at once. An electron can be in a superposition of different positions. An atom can be in a superposition of different energy levels. And a particle can be spinning clockwise and counterclockwise simultaneously. The mathematical framework for describing these quantum states was developed primarily by Werner Heisenberg and Erwin Schrödinger in the mid-1920s. Schrödinger formulated quantum mechanics using wave functions, mathematical objects that encode all the information about a quantum system. The wave function, usually denoted by the Greek letter psi, evolves smoothly and predictably according to the Schrödinger equation. However, the wave function itself isn't directly observable. What we measure are specific properties like position or momentum, and quantum mechanics can only predict the probabilities of different measurement outcomes. When a measurement is made, something dramatic happens to the wave function. It undergoes what's called wave function collapse. Before measurement, the system is in a superposition of many possible states. After measurement, it's found in one definite state, and the wave function instantly changes to reflect this new reality. The probability of collapsing into any particular state is given by the square of the wave function's amplitude for that state. This probabilistic nature of quantum mechanics bothered many physicists, including Einstein, who famously said that God does not play dice with the universe. But countless experiments have confirmed that this randomness is fundamental and irreducible. Quantum mechanics doesn't fail to predict the exact outcome of measurements because we lack information about hidden variables. The universe itself doesn't determine the outcome until the measurement occurs. Before that moment, the outcome genuinely doesn't exist, except as a range of possibilities with associated probabilities. Another cornerstone of quantum mechanics is Heisenberg's uncertainty principle, formulated in 1927. This principle states that certain pairs of properties, called complementary variables, cannot both be known with perfect precision simultaneously. The most famous example involves position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. Mathematically, the product of the uncertainties in position and momentum must be greater than or equal to Planck's constant divided by 4 pi. This uncertainty isn't a limitation of our measurement tools. It's a fundamental feature of reality. A particle simply doesn't have a definite position and definite momentum at the same time. These properties are incompatible in a deep quantum mechanical sense. The uncertainty principle applies to other pairs of variables too. Energy and time form another complementary pair, as do different components of angular momentum. One consequence of the energy-time uncertainty principle is that energy conservation can be violated for very short periods. Particles can borrow energy from the vacuum, so to speak, as long as they pay it back quickly enough that the uncertainty principle isn't violated. This leads to a surprising prediction. Even in completely empty space, in a perfect vacuum, quantum fluctuations are constantly creating and annihilating pairs of particles and antiparticles. These virtual particles exist for only the briefest instance before disappearing, but their effects are real and measurable. They cause tiny shifts in atomic energy levels, and they're responsible for a phenomenon called the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience an attractive force due to the quantum fluctuations in the space between them. The quantum vacuum is far from empty. It's a seething sea of activity at the smallest scales, with particles constantly popping into and out of existence. This might seem like pure theoretical speculation, but the predictions made by quantum field theory about vacuum fluctuations have been tested to incredible precision. The anomalous magnetic moment of the electron, a tiny correction to the electron's magnetic properties caused by virtual particles, has been calculated and measured to agree to better than 1 part in a trillion, making it one of the most precisely verified predictions in all of science. Quantum mechanics also introduces profound changes to our understanding of atomic structure. In the early 20th century, Ernest Rutherford discovered that atoms have a tiny, dense nucleus surrounded by electrons. But classical physics predicted that these orbiting electrons should radiate energy and spiral into the nucleus in a fraction of a second. Obviously, atoms are stable, so something was wrong with the classical picture. The solution came from quantum mechanics. Electrons in atoms can only occupy certain discrete energy levels, like standing waves on a string that only fit certain specific wavelengths. An electron in the lowest energy level, the ground state, cannot lose any more energy because there's no lower level available. It's quantum mechanically stable. When an electron transitions from a higher energy level to a lower one, it emits a photon with energy exactly equal to the difference between the levels. This explains the discrete spectral lines that atoms emit and absorb, patterns that had puzzled scientists for decades. The energy levels in atoms are determined by solving the Schrödinger equation for an electron in the electric field of the nucleus. For the simplest atom, hydrogen, with just 1 electron, the solutions can be found exactly. The electron's wave function spreads out in a cloud around the nucleus, with different shapes for different energy levels. These electron clouds, or orbitals, determine the size and chemical properties of atoms. Understanding atomic structure quantum mechanically allows us to explain the entire periodic table of elements. Each element has a unique number of protons in its nucleus, and in a neutral atom, an equal number of electrons surrounds that nucleus. These electrons fill up the available energy levels starting from the lowest, following rules derived from quantum mechanics. The Pauli exclusion principle, formulated by Wolfgang Pauli in 1925, states that no 2 electrons can occupy exactly the same quantum state. This is why electrons stack up in different orbitals rather than all falling into the lowest energy level. The arrangement of electrons in an atom determines its chemical behavior. Elements with similar electron configurations have similar properties, which is why the periodic table has its characteristic repeating structure. Noble gases have completely filled outer electron shells, making them chemically inert. Alkali metals have a single electron in their outermost shell, which they readily give up, making them highly reactive. All of chemistry, from the bonds between atoms and molecules, to the reactions that power life itself, emerges from the quantum mechanical behavior of electrons. Quantum mechanics doesn't just explain individual atoms. It also governs how atoms combine to form molecules and how those molecules interact. Chemical bonds form when electrons are shared between atoms or transferred from one atom to another, and the strength and geometry of these bonds are determined by quantum mechanics. The double helix structure of DNA, the strength of diamond, the flexibility of proteins, all of these macroscopic properties ultimately derive from quantum effects at the atomic scale. One of the strangest and most powerful predictions of quantum mechanics is the phenomenon of quantum tunneling. In classical physics, if a particle doesn't have enough energy to overcome a barrier, it simply can't get through. But in quantum mechanics, the wave function doesn't go to 0 at the barrier. It extends into and through the barrier region. This means there's a non-zero probability that a particle can appear on the other side of a barrier, even if it doesn't have enough energy to classically surmount it. The particle tunnels through the barrier. This isn't just theoretical curiosity. Quantum tunneling is essential to many physical processes. It's how alpha particles escape from radioactive nuclei during radioactive decay. The alpha particle is trapped inside the nucleus by the strong nuclear force, but it can tunnel through the barrier and escape, which is how we get alpha radiation. The rate of tunneling depends exponentially on the barrier's width and height, which is why different radioactive isotopes have vastly different half-lives, ranging from fractions of a second to billions of years. Tunneling is also crucial to nuclear fusion in stars, including our Sun. For hydrogen nuclei to fuse into helium and release energy, they need to get close enough together for the strong nuclear force to bind them, but they're both positively charged. so they repel each other electrostatically. At the temperatures in the sun's core, about 15 million Kelvin, protons don't have enough energy to overcome this electrostatic barrier through classical means. But quantum tunneling allows them to get close enough to fuse anyway, enabling the nuclear reactions that power the sun and make life on Earth possible. Modern technology relies heavily on quantum tunneling too. Scanning tunneling microscopes use the exponential sensitivity of tunneling currents to distance to map out the positions of individual atoms on surfaces. Electrons tunnel between a sharp metal tip and the surface being studied, and by measuring how the tunneling current changes as the tip moves, scientists can create images with atomic resolution. This technology has allowed us to not only see individual atoms, but also to manipulate them, moving them around to create tiny structures and explore matter at its fundamental level. Flash memory, the storage technology in USB drives and solid-state hard drives, also relies on tunneling. Information is stored as charge trapped on tiny isolated conductors called floating gates. To write data, electrons tunnel through an insulating barrier onto these gates. To erase data, electrons tunnel back off. Without quantum tunneling, this ubiquitous form of data storage wouldn't be possible. Perhaps the most philosophically challenging aspect of quantum mechanics is the phenomenon of quantum entanglement. When two or more particles interact, their quantum states can become correlated in ways that have no classical analog. The particles become entangled, meaning that their properties are linked, regardless of how far apart they may be separated afterward. Measuring a property of one particle instantaneously affects the possible outcomes of measuring the other particle, even if they're on opposite sides of the universe. Einstein, along with Boris Podolsky and Nathan Rosen, pointed out the strangeness of entanglement in a famous 1935 paper. They argued, even more ambitious is the quest to build quantum computers. Classical computers process information in bits, each of which is either 0 or 1. But quantum computers use quantum bits, or qubits, which can be in superpositions of 0 and 1 simultaneously. A system of n qubits can be in a superposition of all 2 to the power of n possible bit strings at once. This allows quantum computers to perform certain types of calculations exponentially faster than classical computers. Quantum algorithms have been developed that could revolutionize computing in specific domains. In 1994, Peter Shor discovered an algorithm that allows a quantum computer to factor large numbers exponentially faster than the best-known classical algorithms. This has profound implications for cryptography, since much of current internet security relies on the difficulty of factoring large numbers. A sufficiently powerful quantum computer running Shor's algorithm could break many of the encryption systems that protect online banking, email, and secure communications. Another important quantum algorithm, discovered by Lofgruve in 1996, provides a quadratic speedup for searching unsorted databases. While not as dramatic as Shor's exponential speedup, Gruve's algorithm demonstrates that quantum computers offer genuine advantages for a broader class of problems. Researchers continue to discover new quantum algorithms for optimization, simulation, and machine learning tasks. Building practical quantum computers is extraordinarily challenging because quantum systems are incredibly fragile. The superposition and entanglement that make quantum computing powerful are easily destroyed by interactions with the environment, a process called decoherence. Even tiny disturbances, stray electromagnetic fields, vibrations, or thermal fluctuations can cause a qubit to lose its quantum properties and behave classically. Modern quantum computers must be isolated in extreme environments, often cooled to temperatures within thousandths of a degree above absolute zero, which is negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. Despite these challenges, progress in quantum computing has been remarkable. Early quantum computers could only maintain coherence for nanoseconds and perform a handful of operations. Today's devices have thousands of qubits and can execute complex algorithms, though they're still prone to errors and require extensive error correction. Major technology companies and research institutions are racing to build more powerful and reliable quantum computers. And while we haven't yet reached the point where quantum computers outperform classical ones for practical problems, that milestone appears to be within reach. The challenge of decoherence affects all quantum systems, not just quantum computers. It's the reason we don't observe quantum effects in everyday life. Macroscopic objects are constantly interacting with countless particles in their environment, rapidly destroying any quantum coherence. A falling leaf, a bouncing ball, a moving car are all subject to quantum mechanics in principle, but their wave functions decohere so quickly that they behave classically for all practical purposes. This raises a fascinating question: how exactly does the classical world emerge from quantum mechanics? If everything is made of quantum particles, why do large objects obey classical laws? The answer involves decoherence, but the details are subtle and still debated. When a quantum system interacts strongly with its environment, information about the system's quantum state spreads into the environment. The system becomes entangled with an enormous number of environmental particles in complex ways that effectively destroy quantum coherence for the system's macroscopic properties. This process happens incredibly quickly for large objects. A dust grain floating in air decoheres in less than a trillionth of a second. For something the size of a cat, the decoherence time would be even shorter. This is why Schrödinger's famous thought experiment about a cat that's simultaneously dead and alive until observed doesn't correspond to reality. The cat is a macroscopic object interacting with its environment in countless ways. It would decohere essentially instantaneously, settling into either the dead or alive state without needing a conscious observer. The role of observation and measurement in quantum mechanics has generated enormous philosophical debate and numerous competing interpretations. The Copenhagen interpretation, developed mainly by Niels Bohr and Werner Heisenberg in the 1920s and 30s, treats measurement as a fundamental process that causes wave function collapse. In this view, quantum mechanics provides complete descriptions of quantum systems, but these descriptions are inherently probabilistic, and measurement creates rather than reveals definite properties. Many physicists have found the Copenhagen interpretation unsatisfying because it treats measurement as special without clearly defining what constitutes a measurement. This led to alternative interpretations. The many worlds interpretation, proposed by Hugh Everett in 1957, eliminates wave function collapse entirely. In this view, all possible measurement outcomes occur, but in different branches of reality. When a measurement happens, the universe splits into multiple versions, one for each possible outcome, and we experience only one branch. While this might sound like science fiction, the many worlds interpretation is taken seriously by many physicists because it's mathematically simple and treats all quantum systems, including measuring devices and observers, consistently using the same quantum rules. It doesn't require special collapse postulates. The main controversy is whether we should believe in the reality of all these parallel worlds that we can never directly observe. Other interpretations include pilot wave theory, where particles have definite positions at all times but are guided by a quantum wave field, and objective collapse theories, which modify quantum mechanics to include spontaneous wave function collapse for large systems. Each interpretation makes the same predictions for experimental outcomes but offers a different picture of underlying reality. After nearly a century, physicists still don't unanimously agree on how to understand what quantum mechanics is telling us about the nature of reality. What's not in dispute is quantum mechanics' extraordinary empirical success. It's been tested more thoroughly than perhaps any other scientific theory, and it's never failed an experimental test. The precision of quantum predictions is staggering. Quantum electrodynamics, the quantum theory of how light and matter interact, predicts the electron's magnetic moment to 15 decimal places, agreeing perfectly with measurements. This level of precision is like predicting the distance from New York to Los Angeles to within the width of a human hair. Quantum mechanics has also led to revolutionary technologies. Lasers, which concentrate light into intense, coherent beams, rely on quantum mechanical stimulated emission. When an atom in an excited state is struck by a photon of the right energy, it drops to a lower energy state while emitting another photon identical to the first. In a laser, this process cascades through many atoms, creating an intense, synchronized light beam. Lasers are now ubiquitous, used in everything from barcode, scanners, and fiber optic communications to surgery and manufacturing. Semiconductors, the foundation of all modern electronics, operate on quantum principles. In a semiconductor, electrons occupy energy bands separated by gaps. By carefully controlling the materials, composition, and structure, engineers can manipulate these band structures to create transistors, diodes, and other components. The smartphones, computers, and countless other electronic devices that pervade modern life all depend on our quantum mechanical understanding of semiconductor physics. Magnetic resonance imaging, or MRI, one of medicine's most valuable diagnostic tools, exploits quantum properties of atomic nuclei. Nuclei have a quantum property called spin, which gives them tiny magnetic moments. When placed in a strong magnetic field, these nuclear spins align with the field and can absorb and emit radio waves at specific frequencies determined by quantum mechanics. By analyzing these signals, MRI machines create detailed images of soft tissues inside the body without using harmful radiation. The development of quantum mechanics also transformed our understanding of light itself. Light exhibits wave-particle duality, behaving as both electromagnetic waves and streams of photons, depending on the experimental context. This duality is captured by quantum field theory, which treats light as excitations of the electromagnetic field. The electromagnetic field permeates all of space, and photons are quantized ripples in this field, much like waves on the surface of a pond, except these waves carry discrete amounts of energy and momentum. Quantum field theory extends quantum mechanics to handle the creation and annihilation of particles. In quantum mechanics, the number of particles is typically fixed, but in quantum field theory, particles can be created and destroyed as long as energy and other conservation laws are satisfied. This framework is essential for describing high-energy processes like those occurring in particle accelerators or the early universe. The Standard Model of Particle Physics, our best current description of fundamental particles and forces, is formulated as a quantum field theory. It describes how quarks and leptons, the building blocks of matter, interact through three fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. Each force is mediated by its own quantum field and associated particles. Photons mediate electromagnetism, W and Z. Bosons mediate the weak force, and gluons mediate the strong force. The Standard Model has been spectacularly successful. It predicted the existence of several particles before they were discovered, including the W and Z bosons found in 1983, the top quark discovered in 1995, and most recently the Higgs boson, detected at the Large Hadron Collider in 2012. The Higgs boson is an excitation of the Higgs field, which permeates all of space and gives mass to other fundamental particles through their interactions with this field. Despite its success, the Standard Model is incomplete. It doesn't include gravity, and it can't explain several observed phenomena like dark matter, dark energy, and the matter-antimatter asymmetry in the universe. Developing a quantum theory of gravity that unifies quantum mechanics with Einstein's general theory of relativity remains one of physics' greatest challenges. Gravity is described by general relativity as the curvature of space-time caused by mass and energy. This geometric picture works beautifully for large-scale phenomena like planetary orbits, black holes, and the expansion of the universe. But when we try to apply quantum mechanics to gravity, we encounter mathematical problems. The resulting theory produces infinite answers for quantities that should be finite, infinities that can't be removed by the usual techniques that work for other forces. String theory is one attempt to resolve this problem. It proposes that fundamental particles aren't point-like, but are actually tiny vibrating strings. Different vibration patterns correspond to different particles, and gravity emerges naturally from this framework. String theory requires extra spatial dimensions beyond the three we observe, dimensions that are presumably curled up so small we can't detect them. While mathematically rich and elegant, string theory has yet to make testable predictions that would distinguish it from other approaches. Loop quantum gravity is another approach that attempts to quantize space-time itself, proposing that space has a discrete structure at the tiniest scales, the Planck length, about 10 to the negative 35 meters. At this scale, space-time isn't smooth, but consists of discrete quantum chunks. Both string theory and loop quantum gravity remain active areas of research, but neither has yet provided a complete and verified theory of quantum gravity. Even without a full theory of quantum gravity, physicists can explore what happens when quantum mechanics and gravity interact in limited contexts. One remarkable prediction comes from combining quantum field theory with curved spacetime. In 1974, Stephen Hawking showed that black holes aren't completely black. Quantum effects near a black hole's event horizon cause it to emit radiation, now called Hawking radiation. the black hole slowly loses mass and eventually evaporates completely. This happens because of quantum fluctuations near the event horizon. Virtual particle and antiparticle pairs constantly form and annihilate in the vacuum. Near a black hole's event horizon, one particle can fall into the black hole while the other escapes. To an outside observer, the black hole appears to be emitting radiation. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the temperature is incredibly low, far below the cosmic microwave background, so they actually absorb more energy than they emit. But tiny black holes would be hot and would radiate away their mass quickly. Hawking radiation has profound implications for fundamental physics because it connects quantum mechanics, gravity, and thermodynamics in unexpected ways. Black holes have entropy proportional to their surface area, and they radiate with a characteristic temperature. This suggests deep connections between information, space-time geometry, and quantum mechanics that we're still trying to fully understand. The black hole information paradox, concerning what happens to information that falls into a black hole, remains one of theoretical physics' most puzzling problems. Quantum mechanics also sheds light on the nature of vacuum and empty space. In classical physics, a vacuum is simply nothing, the absence of matter and energy. But quantum mechanics tells a different story. The uncertainty principle allows energy to fluctuate even in supposedly empty space. These quantum vacuum fluctuations have measurable consequences. They cause the Lamb shift, a tiny difference in energy levels in hydrogen atoms. They create the Casimir force between closely spaced metal plates, and they may even explain the cosmological constant, the mysterious dark energy that's causing the universe's expansion to accelerate. The energy density of quantum vacuum fluctuations, if naively calculated, comes out absurdly large, roughly 10 to the power of 120 times larger than what we observe as dark energy. This is sometimes called the cosmological constant problem, and it's one of the biggest puzzles in theoretical physics. Something is wrong with our calculation or our understanding, but we don't yet know what. It might require a complete quantum theory of gravity to resolve. Quantum mechanics has also revolutionized our understanding of atoms and molecules beyond simple structure. Quantum chemistry uses quantum mechanics to calculate molecular properties, predict chemical reactions, and design new materials. While exact solutions of the Schrödinger equation are only possible for the simplest systems, computational methods allow approximate solutions for complex molecules. These calculations can predict molecular geometries, bond strengths, reaction rates, and spectroscopic properties with impressive accuracy. Pharmaceutical companies use quantum chemistry to design new drugs, predicting how molecules will interact with biological targets before synthesizing them in the lab. Materials scientists use it to design new materials with specific properties, from superconductors to solar cell materials to catalysts for industrial processes. One particularly important quantum phenomenon in chemistry and biology is quantum tunneling of protons and hydrogen atoms. Despite being relatively heavy compared to electrons, protons can tunnel through energy barriers in certain chemical reactions. This affects reaction rates and can be biologically significant. Some enzymes may exploit quantum tunneling to enhance their catalytic activity, allowing biochemical reactions to proceed faster than classical chemistry would predict. There's growing interest in whether quantum effects play important roles in biology beyond basic chemistry. Some researchers have suggested that quantum coherence might be relevant to photosynthesis, the process by which plants and bacteria convert sunlight into chemical energy. In photosynthesis, energy absorbed, the concept of quantum non-locality, demonstrated through entanglement and Bell inequality violations, challenges our intuitions about space and separateness. Einstein's theory of relativity teaches us that no signal or influence can travel faster than light, which is approximately 300 million meters per second, or about 186,000 miles per second. Yet, entangled particles display correlations that seem to require instantaneous coordination across arbitrary distances. This apparent contradiction is resolved by recognizing that while entanglement creates correlations, it cannot be used to send information faster than light. The correlations only become apparent when measurement results from both locations are compared through conventional communication channels. Nevertheless, quantum non-locality represents a profound departure from our classical picture of reality, where objects are separate and independent unless they interact. Through local forces, entangled particles, no matter how far apart, remain part of a single quantum system. In some sense, the separation is illusory. This has led some physicists to suggest that quantum mechanics is telling us something deep about the nature of space itself, that spatial separation might be less fundamental than we think, and that the universe might be more interconnected at a basic level than classical physics suggests. These ideas connect to ongoing attempts to understand the relationship between quantum information and space-time geometry. Some theoretical physicists propose that space-time itself might emerge from quantum entanglement, that the geometry of space and time could be a large-scale manifestation of patterns of quantum information. This would represent a complete inversion of how we usually think about physics, where quantum mechanics operates within the framework of space-time. Instead, space-time would be secondary, arising from more fundamental quantum informational structures. Another area where quantum mechanics reveals surprising physics is in the realm of quantum statistics. In classical physics, particles are distinguishable individuals. Even if two particles are identical, you can, in principle, track which one is which by following their trajectories. But in quantum mechanics, identical particles are truly indistinguishable. The wave function must be either symmetric or antisymmetric under particle exchange, leading to two types of quantum statistics. Particles with half-integer spin, like electrons, protons, and neutrons, are called fermions and obey Fermi-Dirac statistics. The wave function for a system of fermions must be antisymmetric under particle exchange. This leads directly to the Pauli exclusion principle. No two fermions can occupy exactly the same quantum state. This principle is responsible for the structure of the periodic table, the stability of matter, and the existence of white dwarf stars and neutron stars, which are supported against gravitational collapse by quantum mechanical pressure arising from the exclusion principle. Particles with integer spin, like photons and gluons, are called bosons and obey Bose-Einstein statistics. Unlike fermions, multiple bosons can occupy the same quantum state. In fact, bosons prefer to be in the same state, a phenomenon called bosonic bunching. This is why lasers are possible. Many photons occupying the same quantum state create an intense, coherent light beam. It's also responsible for some of the most exotic states of matter known to physics. At extremely low temperatures, typically within a millionth of a degree above absolute zero, a gas of bosonic atoms can undergo Bose-Einstein condensation. All the atoms fall into the same quantum ground state, forming what's essentially a macroscopic quantum object. The first Bose-Einstein condensates were created in 1995 using clouds of rubidium and sodium atoms cooled by lasers and magnetic fields. In a condensate, thousands or millions of atoms behave as a single quantum entity, described by one collective wave function. Bose-Einstein condensates exhibit bizarre properties. They flow without viscosity, a phenomenon called superfluidity. When a condensate is rotated, it doesn't spin uniformly like a classical fluid. Instead, it forms quantized vortices, with circulation only occurring in discrete units determined by Planck's constant. These vortices arrange themselves in regular lattice patterns, directly revealing quantum mechanical effects on macroscopic scales. Superfluidity was actually discovered much earlier in liquid helium-4, which becomes superfluid below 2.17 Kelvin, about -270.98 degrees Celsius. Below this temperature, helium flows without friction, climbs up the walls of containers, and exhibits other bizarre behaviors. This superfluidity arises because helium for atoms are bosons and can form a Bose-Einstein condensate. Helium-3, with one less neutron, is a fermion and doesn't become superfluid until much lower temperatures, where pairs of helium-3 atoms bind together to form bosonic molecules. Superconductivity, the complete disappearance of electrical resistance in certain materials at low temperatures, is another quantum phenomenon related to boson statistics. In conventional superconductors, electrons pair up through interactions with the crystal lattice to form Cooper pairs. These pairs, having integer spin, behave as bosons and can form a condensate that flows without resistance. High-temperature superconductors, discovered in 1986, work at higher temperatures than conventional superconductors, though the mechanism isn't fully understood and likely involves more complex quantum effects. Superconductors have remarkable properties beyond zero resistance. They expel magnetic fields from their interior, a phenomenon called the Meissner effect. This allows superconductors to levitate above magnets, creating frictionless magnetic levitation. Superconductors also support persistent currents that can flow indefinitely without any driving voltage. These properties make superconductors valuable for creating strong electromagnets used in MRI machines, particle accelerators, and potentially for power transmission and magnetic levitation trains. The quantum Hall effect, discovered in 1980, reveals even more exotic quantum phenomena. When a two-dimensional sheet of electrons is subjected to a strong magnetic field at low temperatures, the Hall resistance, measured perpendicular to the current flow, becomes quantized in precise multiples of fundamental constants. The quantization is so precise that the quantum Hall effect is used to define the international standard for electrical resistance. The effect arises from electrons moving in quantized circular orbits in the magnetic field, creating discrete energy levels called Landau levels. An even stranger variant, the fractional quantum Hall effect, was discovered in 1982. Here, the Hall resistance is quantized in fractional multiples, like 1/3 or 2/5. This can't be explained by single electron physics. Instead, electrons in the two-dimensional system interact strongly with each other and form collective quantum states, with quasi-particles carrying fractional electric charge. These quasi-particles aren't fundamental particles, but rather collective excitations of the quantum many-body system, yet they behave in some ways like particles with fractional charge. Some fractional quantum Hall states host even more exotic quasi-particles called anyons, which have quantum statistics that are neither fermionic nor bosonic. When you exchange to anyons, the quantum wave function doesn't just pick up a plus or minus sign, as with bosons and fermions. Instead, it gets multiplied by a complex phase factor. This braiding statistics makes anyons potentially useful for topological quantum computing, a proposed approach to building quantum computers that are inherently protected against certain types of errors. Topology, the mathematical study of properties that remain unchanged under continuous deformations, has become increasingly important in understanding quantum systems. Topological phases of matter have properties that depend on global features of their quantum states rather than local details. These properties are robust against perturbations and imperfections, making them potentially valuable for quantum technologies. Topological insulators are materials that act as insulators in their bulk, but conduct electricity on their surfaces or edges. The surface conduction is protected by topology and can't be eliminated by disorder or impurities that would normally destroy ordinary conductivity. These materials were predicted theoretically in the early 2000s and subsequently discovered in real materials. They represent a new class of matter with unique properties determined by quantum mechanics and topology. The concept of geometric phase or Berry phase reveals another subtle aspect of quantum mechanics. When a quantum system is taken through a cyclic evolution, slowly changing its parameters and returning to the initial configuration, the wave function can acquire a phase factor that depends only on the geometric path taken through parameter space, not on the details of timing or speed. This geometric phase has observable consequences and plays important roles in various quantum phenomena, from the Aharonov-Bohm effect to the quantum Hall effect. Quantum mechanics has also revolutionized our understanding of measurement and information. Claude Shannon's classical information theory, developed in the 1940s, quantifies information in bits and establishes fundamental limits on data compression and communication. Quantum information theory extends these ideas to quantum systems, revealing new possibilities and constraints. A classical bit is either 0 or 1, but a qubit can be in a superposition of 0 and 1. This might suggest that a qubit can store infinite information by encoding it in the continuous parameters of the superposition. However, the Knock-Loening theorem, proved in 1982, shows that arbitrary unknown quantum states cannot be copied. This limits how much information can be extracted from a qubit to at most one classical bit through measurement. Despite this limitation, quantum systems can process and transmit information in ways impossible for classical systems. Quantum teleportation, first demonstrated experimentally in 1997, allows the quantum state of one particle to be transmitted to another distant particle without anything physical traveling between them. This doesn't violate relativity because classical information must be sent conventionally to complete the teleportation, and no information about the quantum state is actually learned in the process. Quantum teleportation relies on entanglement and illustrates how quantum information differs from classical information. The original particle state is destroyed during teleportation, consistent with the no-cloning theorem. The technique has been refined and extended, with quantum states teleported across increasingly large distances, from meters to kilometers to eventually, potentially satellite distances, for global quantum communication networks. Dense coding is another quantum information protocol that allows two classical bits to be transmitted by sending only one qubit, provided the sender and receiver share an entangled pair beforehand. By performing different operations on their half of the entangled pair and sending it to the receiver, the sender can convey 2 bits of information. The receiver then measures both qubits together and can extract both bits. This represents an enhancement in communication capacity made possible by entanglement. Quantum error correction is a crucial development that makes practical quantum computing feasible despite decoherence and errors. Surprisingly, even though quantum states can't be cloned, they can be protected from errors using clever encoding schemes. Information is stored redundantly across multiple qubits in entangled states, such that errors on individual qubits can be detected and corrected without ever learning what information is encoded. This allows quantum computers to operate reliably, despite imperfect components. The development of quantum error correction codes in the mid-1990s was a breakthrough that transformed quantum computing from a theoretical curiosity to a plausible technology. Modern quantum computers implement these codes. Though current systems still have error rates too high for fully fault-tolerant operation, achieving reliable fault-tolerant quantum computation remains a major goal of the field. Beyond computing and communication, quantum metrology exploits quantum effects to make ultra-precise measurements. Quantum properties like superposition and entanglement can enhance measurement sensitivity beyond what's possible classically. Atomic clocks, the most precise timekeeping devices ever built, rely on quantum transitions in atoms. Modern optical atomic clocks are so precise they would gain or lose less than 1 second over the age of the universe. About 14 billion years. These ultra-precise clocks aren't just laboratory curiosities. They enable GPS navigation, which requires precise time synchronization between satellites and receivers. They test fundamental physics theories, measuring tiny effects like gravitational time dilation at different heights or relativistic effects from Earth's motion. They might even detect gravitational waves or dark matter by looking for correlated shifts in separated clocks. Quantum sensors can detect magnetic fields, gravitational fields, rotation, and acceleration with unprecedented sensitivity. Nitrogen vacancy centers in diamond point defects, where a nitrogen atom replaces a carbon atom next to a vacancy, create quantum systems that are sensitive to magnetic fields and can operate at room temperature. These sensors can image magnetic fields at nanometer scales, useful for studying everything from magnetic materials to living cells. Quantum illumination is a proposed radar technique, using entangled photons to detect objects in noisy environments more effectively than classical radar. Even though the entanglement is destroyed by noise and loss, quantum illumination can still provide detection advantages because of correlations in the quantum noise. This could lead to radar systems that can detect stealth aircraft or operate at very low power levels. The study of quantum chaos explores how quantum systems behave when their classical counterparts exhibit chaotic dynamics. Classical chaos involves extreme sensitivity to initial conditions, where tiny differences in starting configuration lead to dramatically different long-term behavior. Quantum mechanics, with its probabilistic nature and linear evolution of the wave function, doesn't permit this kind of sensitive dependence. Yet quantum systems, whose classical limits are chaotic, do show characteristic quantum signatures, including specific patterns in energy level spacing and wave function structure. This connects to fundamental questions about the transition from quantum to classical behavior and the foundations of statistical mechanics, which explains how the microscopic reversible laws of physics give rise to macroscopic irreversible phenomena like heat flow and entropy increase. Quantum chaos and the related field of quantum thermodynamics are active research areas, exploring how thermodynamic laws emerge from quantum mechanics. Quantum mechanics also provides new perspectives on cosmology and the early universe. During the Big Bang's first moments, the universe was incredibly hot and dense, with quantum effects dominating even at cosmic scales. Quantum fluctuations in the early universe, stretched to astronomical sizes by cosmic inflation, may have seeded the formation of galaxies and large-scale structures we observe today. The cosmic microwave background, radiation left over from when the universe became transparent, about 380,000 years after the Big Bang, carries imprints of these quantum fluctuations. Measurements of the cosmic microwave background reveal patterns that match predictions from quantum field theory applied to the early universe with extraordinary precision. This provides a remarkable test of quantum mechanics at scales ranging from subatomic to cosmic. The same quantum principles that govern atoms and molecules also shaped the largest structures in the universe. The implications of quantum mechanics extend to our understanding of time itself. In quantum mechanics, time plays a unique role compared to other variables, like position or momentum. Time is a parameter in the Schrödinger equation, not an observable with its own quantum operator. This asymmetry between time and space in quantum mechanics has puzzled physicists and led to various attempts to formulate quantum mechanics in ways that treat time and space more the arrow of time. The fact that time seems to flow in one direction with past, present, and future being distinct is not explained by the fundamental laws of quantum mechanics, which are time reversible. The arrow of time appears to be connected to the second law of thermodynamics, which states that entropy tends to increase. But how this statistical law emerges from underlying reversible quantum dynamics remains a deep question connecting quantum mechanics, thermodynamics, and cosmology. Quantum decoherence plays an important role in understanding time's arrow. As quantum systems interact with their environments, information spreads irreversibly into the environment, creating effective irreversibility, even though the underlying dynamics are reversible. This decoherence process happens extremely quickly for macroscopic systems and may be responsible for our perception of a flowing present moment and a definite past. The concept of time in quantum gravity becomes even more problematic. In general relativity, time is part of the dynamic space-time geometry. The quantum Zeno effect demonstrates another counterintuitive aspect of measurement. The effect is named after Zeno's paradoxes of motion from ancient Greek philosophy. In quantum mechanics, repeatedly measuring whether a system has changed can actually prevent it from changing. Frequent measurements collapse the wave function back to its initial state, so often that the system doesn't have time to evolve to other states. This effect has been demonstrated experimentally and has potential applications in quantum computing for protecting qubits from unwanted transitions. Conversely, the inverse quantum Zeno effect shows that under certain conditions, frequent measurements can accelerate rather than freeze quantum evolution. The interplay between measurement and dynamics in quantum mechanics continues to reveal surprising phenomena with potential practical applications. Quantum contextuality is another fundamental feature distinguishing quantum from classical physics. It refers to the fact that the result of measuring a quantum observable can depend on which other observables are measured simultaneously. In classical physics, objects have definite values for all their properties regardless of how we measure them, but quantum mechanics denies this. The same quantum observable can have different measurement statistics depending on the measurement context, the set of compatible observables measured alongside it. The Kochen-Specker theorem, proved in 1967, establishes that it's impossible to assign definite pre-existing values to all quantum observables in a way that's consistent with quantum predictions. This rules out a broad class of hidden variable theories and demonstrates that quantum contextuality is fundamental. Experimental tests of contextuality, similar to tests of Bell inequalities, consistently confirm quantum predictions and rule out non-contextual hidden variable models. Quantum contextuality isn't just philosophically interesting, it's been identified as a potential resource for quantum computation, providing quantum advantages for certain computational tasks. Understanding and exploiting contextuality may lead to new quantum algorithms and protocols. The study of open quantum systems that interact with their environments, has become increasingly important. Most real quantum systems aren't perfectly isolated, and their interaction with the environment affects their behavior. The mathematical framework for describing open quantum systems involves density matrices rather than pure state wave functions, and master equations that describe how systems evolve under environmental influence. This framework is essential for understanding decoherence, quantum error correction, and the practical implementation of quantum technologies. It also connects quantum mechanics to thermodynamics, allowing the study of heat flow, work extraction, and entropy production in quantum systems. Quantum thermodynamics has emerged as a vibrant field, exploring how thermodynamic concepts apply at quantum scales and whether quantum effects enable new thermodynamic possibilities. One surprising prediction from quantum thermodynamics is that quantum coherence can be a resource for extracting work from thermal systems. Quantum engines that exploit coherence and entanglement might achieve efficiencies or power outputs beyond what's possible for classical heat engines. While these ideas are mostly theoretical, they're beginning to be tested in laboratory systems. Maxwell's Demon, a thought experiment from classical thermodynamics about a hypothetical being that could violate the second law by sorting molecules, takes on new dimensions in quantum mechanics. Quantum versions of Maxwell's Demon have been proposed and even experimentally realized, showing how information and quantum correlations relate to thermodynamic quantities like entropy and free energy. Quantum simulation is an important application of quantum systems to study other quantum systems. Richard Feynman proposed in 1982 that quantum computers would be naturally suited for simulating quantum mechanics. Since classical computers struggle to simulate quantum systems due to the exponential growth of required resources with system size, a quantum simulator uses one controllable quantum system to mimic the behavior of another quantum system that's difficult to study directly. This approach has already proven valuable. Cold atom systems have simulated various quantum models, revealing phase transitions and exotic states of matter that are difficult to study theoretically or in natural materials. Trapped ions, superconducting circuits, and other quantum platforms serve as quantum simulators for condensed matter, physics, quantum chemistry, and even aspects of high-energy physics. Some quantum simulations have addressed fundamental physics questions. Quantum simulators have studied the dynamics of thermalization in isolated quantum systems, tested quantum versions of phase transitions, and explored phenomena related to quantum field theory. As quantum simulation platforms improve, they're becoming valuable tools for discovering new physics in regimes inaccessible to classical computation or direct experiment. The concept of quantum supremacy or quantum advantage refers to quantum computers performing tasks that classical computers cannot do in reasonable time. In 2019, Google announced achieving quantum supremacy by performing a specific calculation in minutes that would take classical supercomputers thousands of years. While the practical utility of this particular calculation is debated, it demonstrated that quantum computers can outperform classical ones for carefully chosen problems. Subsequent work has continued pushing quantum advantage, with quantum computers tackling increasingly practical problems in optimization, machine learning, and simulation. While we haven't yet reached the point where quantum computers provide clear advantages for important real-world problems, steady progress suggests this may happen within years. Quantum machine learning explores how quantum computing might enhance artificial intelligence and data analysis. Quantum algorithms for machine learning could potentially process data faster or find better solutions than classical algorithms for certain tasks. Proposals include quantum versions of neural networks, quantum support vector machines, and quantum algorithms for clustering and dimensionality reduction. The field is still nascent, and it's unclear which machine learning tasks will see genuine quantum advantages. Some proposed quantum machine learning algorithms have been found to offer less speed-up than initially hoped, or to have classical competitors that perform comparably. But the intersection of quantum computing and machine learning remains an exciting research frontier with potential for breakthrough applications. Quantum networks aim to connect quantum computers and other quantum devices across distances, enabling distributed quantum computing and secure quantum communications. Building such networks requires quantum repeaters to extend quantum communication beyond the limited distances achievable with direct transmission. Quantum repeaters used entanglement, swapping, and quantum memories to create long-distance entanglement from shorter entangled links. Satellite-based quantum communication has made remarkable progress. China's Michia satellite, launched in 2016, demonstrated quantum key distribution and entanglement distribution over distances exceeding 1,000 kilometers. These achievements prove that global quantum networks using satellite links are feasible, opening possibilities for intercontinental quantum communication and potentially worldwide. Quantum Internet infrastructure. A full quantum internet would allow not just secure communication, but also distributed quantum computing, where multiple quantum computers work together on problems, and networked quantum sensors that share entanglement for enhanced precision. Such capabilities could enable fundamentally new applications we haven't yet imagined. The philosophical and interpretational debates around quantum mechanics show no signs of ending. New interpretations continue to be proposed, and existing ones are refined. Relational quantum mechanics suggests that quantum states are relative to observers rather than absolute. Cubism, or quantum Bayesianism, interprets quantum states as representing personal degrees of belief rather than objective physical states. These interpretations emphasize the role of agents and information in quantum mechanics. Objective collapse theories modify quantum mechanics to include spontaneous collapse of wave functions for large systems, eliminating the measurement problem by making collapse a physical process that happens spontaneously when systems become sufficiently large or complex. These theories make predictions slightly different from standard quantum mechanics, potentially allowing experimental tests to distinguish them. Despite interpretational disagreements, physicists agree on the practical rules for using quantum mechanics to make predictions. This pragmatic approach has enabled incredible technological and scientific progress, even without consensus on what quantum mechanics means. Some argue that seeking a single correct interpretation is misguided, that different interpretations are just different languages for describing the same physical reality. Others maintain that interpretational questions are important because they might guide us toward deeper theories. The search for quantum gravity, for example, might be informed by how we understand quantum measurement and the role of space-time in quantum theory. Interpretational debates can motivate new experiments and new formulations of quantum mechanics that revealed previously hidden aspects of the theory. Quantum mechanics continues to surprise us nearly a century after its development. New quantum phenomena are discovered regularly, from topological phases of matter to time crystals, systems that exhibit periodic behavior in their ground state despite having no energy input. These discoveries expand our understanding of what quantum mechanics allows and sometimes challenge our expectations based on classical intuition. Time crystals, first proposed in 2012 and experimentally realized in 2017, represent a new phase of matter where time translation symmetry is spontaneously broken. Just as ordinary crystals have structure that repeats in space, time crystals have dynamics that repeat in time even in their lowest energy state. They exist out of equilibrium and require periodic driving to maintain their temporal periodicity. The existence of time crystals demonstrates that our catalogue of possible phases of matter is far from complete. They also illustrate how quantum mechanics continues to reveal new physics even in well-studied areas. The boundary between equilibrium and non-equilibrium quantum systems, the role of symmetry breaking in quantum phases, and the possibilities for many-body quantum dynamics remain rich areas for discovery. Quantum mechanics has also transformed our understanding of chemistry beyond calculating molecular structures. Quantum effects influence reaction pathways, molecular dynamics, and the behavior of materials. Tunneling allows chemical reactions to proceed at lower temperatures than classical predictions suggest, which is crucial for chemistry in cold environments, like interstellar space, where complex molecules form despite temperatures near absolute zero. Quantum coherence may play roles in biological energy transfer, as mentioned earlier with photosynthesis. Beyond photosynthesis, researchers have proposed quantum effects in enzyme catalysis, where tunneling and quantum mechanical nuclear motion might enhance reaction rates. Olfaction, our sense of smell, has been hypothesized to involve quantum tunneling of electrons within odor receptors. Though this remains controversial and debated, the magnetic compass sense in birds likely involves quantum entanglement, making it one of the clearest examples of quantum biology. Cryptochrome proteins in bird retinas contain pairs of radicals whose chemical fate depends on magnetic field orientation through a mechanism involving spin dynamics and entanglement. This quantum compass would be remarkable not just for using entanglement, but for maintaining it long enough in a biological environment to be functionally useful. If quantum effects are widespread in biology, It suggests that evolution has found ways to exploit quantum mechanics for functional advantage. Understanding how biological systems maintain quantum coherence despite thermal noise and environmental disturbance could inspire new approaches to building quantum technologies. Nature may have solved problems in quantum control and error mitigation that engineers are still struggling with. The foundations of quantum mechanics connect to fundamental questions in mathematics and logic. Quantum logic, developed by Garrett Birkhoff and John von Neumann in the 1930s, shows that the logical structure underlying quantum mechanics differs from classical Boolean logic. In classical logic, propositions are either true or false, and logical operations, like AND/OR, are and not follow familiar rules. Quantum logic relaxes some of these rules, reflecting the fact that quantum propositions can be incompatible, unable to be simultaneously true or false. This mathematical structure is captured by the algebra of projection operators in Hilbert's space, the mathematical framework for quantum mechanics. The fact that quantum mechanics requires a different logical structure suggests it's revealing something fundamental about the continuity of reality and how propositions about physical systems relate to each other. Category theory, a branch of abstract mathematics dealing with structures and relationships between structures, has been applied to quantum mechanics and quantum information. Categorical quantum mechanics provides a graphical language for reasoning about quantum systems and processes using diagrams rather than traditional equations. This approach has revealed deep connections between quantum mechanics, logic, computation, and information theory. These mathematical explorations aren't just abstract exercises. They can lead to new quantum algorithms, new ways of thinking about quantum error correction, and insights into the structure of quantum theories. The interplay between physics and mathematics has always been fertile, and quantum mechanics provides particularly rich territory for this interaction. Quantum field theory, the framework combining quantum mechanics and special relativity, describes all known fundamental particles and forces except gravity. It treats particles as excitations of underlying quantum fields permeating spacetime. The electromagnetic field, electron field, quark fields, and others all exist throughout space, and what we call particles are quantized vibrations in these fields. This perspective unifies our understanding of matter and forces. Forces arise from particles exchanging virtual particles, temporary quantum fluctuations. Electrons repel because they exchange virtual photons. Quarks inside protons and neutrons are bound by exchanging virtual gluons. The weak force that causes radioactive decay involves W and Z bosons. All these interactions emerge from quantum field theory's mathematical structure. Quantum field theory makes extraordinarily precise predictions. The anomalous magnetic moment of the electron, mentioned earlier, is calculated by summing contributions from virtual particles interacting in increasingly complex ways. These calculations involve Feynman diagrams, pictorial representations of particle interactions invented by Richard Feynman in the 1940s. Each diagram represents a mathematical term in the calculation, and summing all diagrams up to a given complexity yields predictions matching experiments to 15 decimal places. This precision comes at a cost. Quantum field theory calculations often produce infinite results that must be removed through a process called renormalization. This involves carefully redefining parameters like mass and charge to absorb infinities while keeping physical predictions finite. Renormalization was initially viewed with suspicion as mathematical trickery, but it's now understood as a systematic procedure revealing how physics changes with scale. Renormalization group theory, developed in the 1970s, shows how physical laws transform when examined at different energy scales or length scales. This framework has applications far beyond particle physics, explaining critical phenomena in phase transitions, the behavior of turbulence, and the emergence of effective theories at different scales throughout physics. The renormalization group reveals why physics is possible despite our ignorance of ultimate fundamental laws. Even if physics at the Planck scale, where quantum gravity effects dominate, is completely different from our current theories, those differences don't affect low-energy phenomena we can study. Physics at different scales decouples, allowing us to make accurate predictions without knowing everything. Effective field theory formalizes this idea, describing physics at a given energy scale using the relevant degrees of freedom. At that scale, while ignoring irrelevant details from higher energies, the standard model itself is likely ineffective. The workforce development challenges for quantum technologies are significant. Quantum engineering requires expertise spanning physics, computer science, electrical engineering, and mathematics. Universities are developing quantum science and engineering programs, but the growing quantum industry's demand for skilled workers outpaces current educational output. Quantum literacy for the broader public also becomes important as quantum technologies enter everyday life. Quantum technology's economic impact could be substantial. Quantum computing might enable new materials and drug discovery, optimize complex systems, enhance artificial intelligence, and solve problems currently intractable. Quantum sensing could revolutionize navigation, medical diagnostics, and resource exploration. Quantum communication ensures security for critical infrastructure and sensitive communications. Governments and companies worldwide are investing billions in quantum research and development. International competition and cooperation in quantum technologies create complex dynamics. Quantum technologies have both civilian and military applications. Quantum-enhanced sensors could detect submarines or stealth aircraft. Quantum computers could break military codes. Quantum communication could secure military communications. This dubious nature creates tensions between scientific openness and national security concerns. At the same time, quantum science remains fundamentally international. Researchers collaborate across borders, and many important discoveries involve multinational teams. The benefits of quantum technologies, from medicine to communication to computation, are potentially universal. Finding balance between cooperation and competition, between openness and security, will be challenging as quantum technologies mature. The timeline for quantum technologies' impact varies by application. Quantum communication and some quantum sensing applications are already commercially available. More sophisticated quantum sensors and expanded quantum networks might emerge within 5 to 10 years. Practical quantum computing for important problems might require 10 to 20 years, though predictions are uncertain. Quantum simulation might achieve practical applications sooner than general quantum computing. Despite the excitement around applications, many quantum researchers remain motivated primarily by curiosity about nature. Understanding quantum mechanics more deeply, testing it in new regimes, and exploring its implications continue driving much research. The interplay between fundamental questions and practical applications has always characterized physics, and quantum mechanics exemplifies this particularly well. Quantum mechanics has taught us that reality is far stranger than our everyday experience suggests. Particles exist in superposition. Measurement affects what's measured. Entangled systems share correlations that defy classical explanation, and uncertainty is fundamental, rather than a limitation of knowledge. These insights have transformed not just physics, but our broader understanding of nature, causality, information, and the relationship between observers and reality. The quantum world operates by rules completely different from the classical world we evolved to navigate. Our intuitions, shaped by macroscopic experience, often mislead us when thinking about quantum phenomena. Developing quantum intuition requires mathematical training, careful experimentation, and willingness to accept that nature doesn't conform to our preconceptions. Yet quantum mechanics is not arbitrary or unintelligible. It has elegant mathematical structure, deep symmetries, and profound connections to other areas of mathematics and physics. The theory's internal consistency and extraordinary empirical success suggest it captures something essential about reality's nature. What exactly that is remains philosophically contested, but the physical content is clear and confirmed by countless experiments. Looking forward, quantum mechanics will undoubtedly continue revealing surprises. New phenomena, new applications, and new theoretical insights await discovery. The quantum frontier extends from the Planck scale, where quantum gravity becomes important, to potentially macroscopic scales, where quantum effects might be observable in specially prepared systems. Between these extremes lies vast, unexplored territory. The quest to understand quantum mechanics' relationship with general relativity remains one of physics' central challenges. These two pillars of 20th century physics have proven extraordinarily successful in their respective domains. Quantum mechanics governs the atomic and subatomic world with incredible precision. General relativity describes gravity, space-time curvature, and cosmology with equal success. yet they seem fundamentally incompatible, using different mathematical frameworks and conceptual foundations. Attempts to simply apply quantum mechanics to gravitational fields lead to mathematical inconsistencies. Unlike other forces, gravity involves the structure of spacetime itself, making quantization conceptually and technically difficult. At low energies, quantum field theory on curved spacetime provides an effective description, treating spacetime as a classical background on which quantum fields propagate. This approach works well for many phenomena, including Hawking radiation and quantum effects in the early universe. But at the Planck scale, where both quantum effects and gravitational curvature become strong, this approximation breaks down. The Planck length, about 10 to the negative 35 meters, and Planck time, about 10 to the negative 44 seconds, represent the scales where quantum gravity becomes essential. At these scales, spacetime itself likely exhibits quantum properties, possibly becoming discrete or foam-like, rather than smooth and continuous. String theory proposes that fundamental entities are not point particles, but tiny one-dimensional strings. Different vibration modes of these strings correspond to different particles, including a massless spin-2 particle identified with the graviton, the hypothetical quantum of gravity. String theory naturally incorporates gravity and unifies it with other forces within a consistent quantum framework. The theory requires extra spatial dimensions, typically 6 or 7 beyond our familiar 3, which must be compactified in specific ways. The mathematical richness of string theory is undeniable, revealing deep connections between seemingly unrelated areas of mathematics and physics. The ADS-CFT correspondence, or holographic principle, discovered within string theory, relates gravitational theories in certain curved spacetimes to quantum field theories on the boundary of those space. This duality suggests profound connections between gravity, quantum mechanics, and information theory. However, string theory faces significant challenges. It makes few testable predictions at accessible energies. The theory has many possible solutions, perhaps 10 to the power of 500 or more, each corresponding to different ways of compactifying extra dimensions and different low-energy physics. This vast landscape of solutions makes it difficult to extract unique predictions. Critics argue string theory has become more mathematical framework than physical theory, lacking the direct connection to experiment that characterizes successful physics theories. Loop quantum gravity takes a different approach, attempting to quantize general relativity directly without introducing extra dimensions or new fundamental objects. It proposes that space has a discrete structure at the Planck scale, with spacetime geometry built from quantum chunks called spin networks. These networks evolve in discrete steps, creating spin foams that represent quantum spacetime dynamics. Loop quantum gravity has achieved notable successes, including removing the singularity at the Big Bang in some models, replacing it with a quantum bounce from a previous contracting phase. The theory makes some testable predictions, though observing effects at the Planck scale remains extraordinarily difficult. Like string theory, loop quantum gravity is incomplete, lacking a full formulation that clearly recovers general relativity in the classical limit, while making definite quantum gravity predictions. Other approaches to quantum gravity include causal set theory, which treats spacetime as a discrete set of events with causal relationships. Asymptotic safety, which proposes that gravity becomes well behaved at high energies due to a non-trivial fixed point of the renormalization group. And emergent gravity proposals, which suggests gravity isn't fundamental but arises from underlying quantum degrees of freedom. Perhaps related to entanglement, the question of whether spacetime is fundamental or emergent is profound. In classical and quantum field theory, spacetime is the stage on which physics unfolds, but quantum gravity hints that spacetime itself might be emergent, arising from something more fundamental. This would represent a radical revision of our physical worldview, comparable to recognizing that solid matter emerges from atoms and quantum mechanics. Quantum entanglement might play a crucial role in spacetime's structure. The ER=EPR conjecture proposes that entangled particles are connected by non-traversable wormholes, geometric structures in spacetime. If true, this would intimately connect quantum entanglement with spacetime geometry, suggesting that the fabric of spacetime is woven from quantum correlations. These ideas connect to the holographic principle, which proposes that all information in a volume of space can be encoded on the volume's boundary. This principle, inspired by black hole thermodynamics, suggests that our three-dimensional reality might be a kind of projection of information encoded on a two-dimensional surface. While seemingly bizarre, the holographic principle has mathematical support from string theory and other approaches, and it might be fundamental to quantum gravity. Black holes remain crucial testing grounds for quantum gravity ideas. They're regions where both quantum effects and strong gravity are important, making them natural laboratories for quantum gravity theories. Understanding what happens to information that falls into black holes, whether it's destroyed or preserved, requires quantum gravity. The information paradox arises because Hawking radiation appears thermal and random, suggesting information is lost, violating quantum mechanics. Recent work suggests information might be preserved through subtle correlations in Hawking radiation, possibly encoded in entanglement structure. The page time, when a black hole has radiated away half its initial mass, appears to mark a transition where information begins returning in Hawking radiation. These insights come from combining quantum information theory with gravity in new ways, suggesting progress toward resolving the information paradox. Quantum gravity might also explain the universe's origin. The Big Bang singularity, where general relativity predicts infinite density and temperature, likely requires quantum gravity for proper description. Quantum cosmology applies quantum mechanics to the universe as a whole, describing the universe's wave function. While speculative, these approaches might explain how the universe began, whether time existed before the Big Bang, and what determined the initial conditions that led to our observed universe. The concept of the multiverse, multiple disconnected or causally separated universes, arises in several contexts including quantum mechanics, cosmology, and string theory. In quantum mechanics, the many worlds interpretation suggests every quantum measurement creates branching universes. In cosmology, eternal inflation generates infinitely many pocket universes with different properties. In string theory, the landscape of solutions might be realized in different regions, creating a multiverse of diverse physics. If the multiverse exists, it has profound implications for physics and philosophy. Some physics questions might lack unique answers because different universes have different properties. The values of fundamental constants, which seem arbitrary and finely tuned in our universe, might simply reflect anthropic selection. We observe a universe compatible with our existence. Critics argue the multiverse is unfalsifiable and therefore unscientific, while proponents claim it's a legitimate consequence of successful theories. Observable consequences of quantum gravity are difficult to identify but not impossible. Quantum gravity effects might leave imprints in the cosmic microwave background, modify the propagation of high-energy particles from distant astrophysical sources, or affect the polarization of light that has traveled cosmological distances. Detecting these tiny effects requires extraordinarily sensitive measurements, but advancing technology makes some tests feasible. Tabletop experiments might also probe quantum gravity regimes. Proposals exist for measuring gravitational interactions between small masses and quantum superposition, testing whether gravity behaves quantum mechanically or collapses superpositions, as some theories suggest. These experiments are at the edge of current technology, but might become feasible within decades, potentially revealing whether gravity is fundamentally quantum. The interplay between quantum mechanics, information theory, and gravity suggests deep connections we're only beginning to understand. Information appears fundamental to quantum mechanics through concepts like entanglement, entropy, and quantum channels. It's also fundamental to black hole physics through the Bekenstein-Hawking entropy formula relating black hole entropy to horizon area. These connections hint that information might be as fundamental as energy, space, or time. Quantum information theory provides new tools for understanding physical systems. Entanglement measures quantify quantum correlations. Quantum channel capacities determine information transmission limits. Quantum error correction reveals how information can be protected. These concepts, developed for quantum communication and computation, are increasingly applied to fundamental physics questions, from quantum gravity to condensed matter physics. The study of quantum complexity, measuring how difficult quantum states are to prepare or operations are to implement, has revealed surprising connections to black hole physics. The complexity of black hole interiors appears to grow for exponentially long times, much longer than thermalization times. suggesting complexity captures aspects of black hole physics missed by traditional approaches. This has led to conjectures connecting quantum circuit complexity to space-time volume in holographic theories. Quantum chaos, mentioned earlier, connects to black hole physics through the idea that black holes are the fastest scramblers in nature. Scrambling refers to how quickly information spreads through a quantum system, becoming encoded in global correlations rather than local observables. Black holes scramble information at a rate set by their temperature and fundamental constants, providing a speed limit for information processing in quantum systems. These connections between quantum information, quantum gravity, and black hole physics suggest that information processing and computational perspectives might be essential for understanding quantum gravity. Some researchers propose that space-time and gravity emerged from quantum information dynamics, with Einstein's equations arising as thermodynamic statements about entanglement, entropy. The foundations of quantum mechanics continue generating new mathematics and physics. Quantum contextuality, non-locality, and other quantum features have inspired new mathematical structures and theorems. Quantum information theory has revealed operational frameworks for understanding quantum mechanics based on what can be done with quantum systems, rather than trying to interpret what quantum states really are. Categorical quantum mechanics provides abstract frameworks for quantum theory, revealing deep structural features. Algebraic quantum field theory axiomatizes quantum field theory rigorously, providing mathematical foundations for understanding the theory's conceptual structure. These mathematical developments both clarify existing quantum theories and point toward possible generalizations or modifications. Generalized probabilistic theories explore what theories beyond quantum mechanics might look like while preserving certain physical principles. This program has identified quantum mechanics as distinguished by specific information theoretic properties, suggesting these properties might be more fundamental. The foundations of statistical mechanics, explaining why isolated systems evolve toward thermal equilibrium despite having reversible microscopic dynamics, connect to quantum mechanics through the eigenstate thermalization hypothesis. This hypothesis proposes that individual energy eigenstates of complex quantum systems encode thermal properties, explaining thermalization without requiring truly random dynamics. The hypothesis has been tested in various quantum systems, including through quantum simulation experiments, quantum many-body physics studies, systems of many interacting quantum particles, a regime where new collective phenomena emerge that aren't present in few particle systems. High-temperature superconductivity, quantum spin liquids, and topological phases are examples of emergent many-body phenomena. Understanding these systems requires going beyond studying individual particles to understanding collective quantum behavior. Strongly correlated quantum systems, where interactions between particles are strong compared to kinetic energy, exhibit particularly rich and complex behavior. Classical intuition often fails completely for these systems. Exact solutions are rarely possible, and even approximate methods struggle. Quantum simulation, using one controllable quantum system to model another, offers a promising approach to understanding strongly correlated systems. Tensor network methods provide powerful tools for studying quantum many-body systems. These methods represent quantum states using networks of tensors, mathematical objects encoding how quantum correlations are structured. Matrix product states and projected entangled pair states are examples of tensor network structures capturing important classes of quantum states efficiently. These methods have revealed organizing principles for quantum phases and enabled simulations of larger systems than previously possible. Quantum field theory, despite being one of physics' most successful frameworks, still holds mysteries and challenges. Non-perturbative phenomena, effects that can't be understood through small perturbations around simple solutions, are often poorly understood. Confinement in quantum chromodynamics, the theory of strong nuclear force, is one example. Quarks and gluons are never observed in isolation, but are always confined within composite particles like protons. Understanding this confinement from first principles remains challenging despite decades of effort. Asymptotic freedom, the discovery that strong force interactions become weaker at high energies, earned David Gross, David Politzer, and Frank Wilczek the 2004 Nobel Prize in Physics. This behavior, opposite to most forces, explains why quarks behave almost freely inside protons at high energies, but are strongly confined at low energies. Computing how this crossover occurs and understanding confinement quantitatively requires sophisticated methods including lattice quantum chromodynamics, which discretizes spacetime to enable numerical calculations. Quantum field theory's mathematical foundations remain incomplete despite the theory's empirical success. Rigorously constructing interacting quantum field theories in 4 spacetime dimensions remains an unsolved problem in mathematical physics. Constructive quantum field theory aims to place quantum field theory on rigorous mathematical footing, but only free theories and certain simplified interacting theories have been rigorously constructed in 4 dimensions. The standard model of particle physics, our best current quantum field theory of fundamental particles and forces, has passed every experimental test for decades. The discovery of the Higgs boson in 2012 completed the standard model, confirming its predictions. Precision measurements of particle properties agree with standard model predictions to remarkable accuracy, sometimes better than 1 part in a billion. Yet the standard model is clearly incomplete. It doesn't include gravity, doesn't explain dark matter or dark energy, doesn't explain why neutrinos have mass or why that mass is so much smaller than other particles, and doesn't explain the matter-antimatter asymmetry in the universe. The values of its parameters, like particle masses and interaction strengths, appear arbitrary and fine-tuned, suggesting deeper principles might determine them. Grand unified theories attempt to unify the electromagnetic, weak, and strong forces into a single force at high energies. These theories predict that interaction strengths converge at very high energies, around 10 to the 16th GeV, far beyond current experimental reach. They also typically predict proton decay, which hasn't been observed despite sensitive experiments. The proton's lifetime must exceed about 10 to the 34 years based on current limits, constraining unified theories. Supersymmetry, if it exists, would help unify forces by ensuring their interaction strengths converge more precisely. It would also provide natural dark matter candidates and help address the hierarchy problem. But as mentioned earlier, no supersymmetric particles have been discovered despite extensive searches. This doesn't rule out supersymmetry, as superpartners might be too heavy for current experiments, but it constrains the theory significantly. The hierarchy problem asks why the weak force, with characteristic energy scale around 100 GeV, is so much stronger than gravity, with characteristic scale at the Planck energy around 10 to the 19th GeV. This enormous ratio, about 10 to the 17th, seems unnatural. Quantum corrections should drive the Higgs boson mass toward the Planck scale, unless extraordinary metioning cancels these corrections to 1 part in 10 to the 34. Supersymmetry or extra dimensions might explain this hierarchy. Or perhaps the hierarchy is environmental, selected by anthropic reasoning in a multiverse. Alternatively, new physics at the TeV scale, just beyond current experimental reach, might stabilize the hierarchy. Ongoing experiments at the Large Hadron Collider and future colliders search for evidence that might resolve this puzzle. Neutrino physics presents several mysteries. Neutrinos have mass, demonstrated by neutrino oscillations, where neutrinos change between different flavors as they propagate. This requires modifying the standard model, which originally assumed massless neutrinos. But neutrino masses are extraordinarily small, millions of times smaller than electron mass. Why neutrino masses are so small remains unexplained. Neutrinos might be Majorana particles, identical to their own antiparticles, unlike other fermions which are distinct from their antiparticles. If so, lepton number isn't conserved, and neutrinoless double beta decay, where a nucleus emits 2 electrons but no neutrinos, should occur. Experiments search for this rare process, which would reveal fundamentally new physics beyond the standard model and might explain why the universe contains matter, but virtually no antimatter. The matter-antimatter asymmetry is one of cosmology's great puzzles. The Big Bang should have produced equal amounts of matter and antimatter, which would have annihilated, leaving a universe of pure energy. Yet the universe is dominated by matter with virtually no antimatter. Understanding how this asymmetry arose requires physics beyond the standard model, likely involving processes in the early universe when temperatures and energies were extreme. Baryogenesis, the generation of matter excess over antimatter, requires 3 conditions identified by Andrei Sakharov in 1967: baryon number violation, CNCP violation, and departure from thermal equilibrium. The Standard Model satisfies these conditions, but produces far too small an asymmetry to explain observations. Extensions of the Standard Model or new physics at high energies might provide the necessary additional sources of asymmetry. Dark matter, comprising about 27% of the universe's mass energy, has been detected only through its gravitational effects. It doesn't emit, absorb, or reflect light, and it doesn't interact via strong or electromagnetic forces. Many observations from galactic rotation curves to gravitational lensing to the cosmic microwave background confirm dark matter's existence, but its nature remains mysterious. Numerous dark matter candidates have been proposed. Weakly interacting massive particles, or WIMPs, were long favored candidates that would interact via weak nuclear force and gravity. Extensive searches using ultrasensitive detectors deep underground have found no evidence for WIMPs, constraining their possible properties. Ixions, light particles proposed to solve another problem in quantum chromodynamics, are another candidate. Searches using resonant microwave cavities and other techniques continue. Primordial black holes, formed in the early universe rather than from stellar collapse, could comprise some or all dark matter. Gravitational wave observations have detected black holes in the mass range that could be primordial, though whether they are abundant enough to explain dark matter remains unclear. Other exotic proposals include sterile neutrinos, dark photons, and more speculative ideas. Dark energy, comprising about 68% of the universe's mass energy, is even more mysterious than dark matter. It appears as a smoothly distributed energy density, causing the universe's expansion to accelerate. Its properties are consistent with a cosmological constant, equivalent to energy density in empty space itself. But this raises the cosmological constant problem mentioned earlier. Alternative explanations for cosmic acceleration include modified gravity theories that change general relativity on cosmological scales, or dynamical dark energy, where the energy density changes over time rather than being constant. Observations increasingly favor a cosmological constant, but alternatives aren't ruled out. Understanding dark energy might require fundamental advances in quantum gravity or new physics beyond both quantum mechanics and general relativity. The early universe provides a laboratory for quantum mechanics under extreme conditions. During cosmic inflation, a brief period of exponential expansion in the universe's first moments, quantum fluctuations were stretched to cosmic scales, seeding structure formation. These quantum fluctuations, originating at subatomic scales, grew to become galaxies and galaxy clusters. The cosmic microwave background preserves an image of these primordial quantum fluctuations. Inflation solves several cosmological puzzles, including the horizon problem, explaining why widely separated regions of the universe have nearly identical properties despite never being in causal contact, and the flatness problem, explaining why the universe's geometry is so close to flat. Inflation predicts specific patterns in cosmic microwave background fluctuations that have been observationally confirmed, providing strong, though not conclusive evidence for the theory. Quantum fluctuations during inflation also predict gravitational waves, ripples in spacetime itself that would leave distinctive patterns in the cosmic microwave background's polarization. Detecting these primordial gravitational waves would confirm inflation and probe physics at energy scales around 10 to the 16th GeV, far beyond particle accelerator capabilities. Several experiments search for this signal, though claims of detection in 2014 were later attributed to dust contamination rather than primordial gravitational waves. The multiverse concept connects to inflation through eternal inflation, where quantum fluctuations cause some regions to continue inflating while others stop, creating a fractal structure of inflating and non-inflating regions. Each pocket universe might have different effective laws of physics, realized from different vacuum states of the underlying theory. This vast multiverse would contain regions with all possible physical properties allowed by the fundamental theory. Anthropic reasoning in the multiverse context suggests we observe physical constants compatible with our existence not because these values are fundamental but because we couldn't exist in regions with different values. For instance, if the cosmological constant were much larger, galaxies couldn't form. If the strong nuclear force was slightly weaker, atomic nuclei would be unstable. These apparent fine-tunings might reflect observational selection rather than fundamental physics. Critics argue that anthropic reasoning is unfalsifiable and represents giving up on finding fundamental explanations. Proponents countered that if the multiverse is real, a consequence of successful theories like inflation and string theory, then anthropic reasoning is scientifically legitimate. The debate touches deep questions about what constitutes scientific explanation and whether all observed properties of our universe must have fundamental explanations. Quantum mechanics in curved space-time, combining quantum field theory with general relativity's curved space-time without quantizing gravity itself, reveals fascinating phenomena. The Unruh effect predicts that an accelerating observer experiences a thermal bath of particles, even in a vacuum, as measured by an inertial observer. The temperature is proportional to acceleration, connecting acceleration, temperature, and quantum vacuum fluctuations in unexpected ways. This effect relates to Hawking radiation through the equivalence principle. Near a black hole's event horizon, an observer hovering at fixed position undergoes constant acceleration to avoid falling in. This acceleration produces thermal radiation analogous to the Unruh effect, explaining Hawking radiation from an accelerated observer's perspective. These connections suggest deep relationships between thermodynamics, gravity, and quantum mechanics. The holographic principle, mentioned earlier, has profound implications for quantum gravity and information. It suggests that physics in any region of space is fully encoded on that region's boundary, with 1 bit of information per Planck area. This implies the universe's information content is much less than naively expected, as information scales with surface area rather than volume. The principle seems to be telling us something fundamental about space-time and quantum information. Black hole complementarity addresses the information paradox by proposing that information is both reflected at the horizon, seen by external observers, and passes through the horizon, experienced by infalling observers. These descriptions seem contradictory, but complementarity argues both are valid from their respective reference frames, somewhat like how relativity reconciles different observers' descriptions. Whether this resolves the paradox or merely restates it remains debated. Recent insights suggest black holes have more structure than previously thought. The black hole interior might be connected to exterior radiation through quantum entanglement in complex ways. Studying entanglement entropy of radiation as a black hole evaporates reveals that information begins returning around the page time, suggesting the interior and radiation are intimately connected through quantum correlations that restore quantum error correction provides analogies for understanding how information escapes from black holes. In quantum error correction, information is encoded redundantly in entangled states such that it can be recovered even if parts of the system are lost or corrupted. Black holes might similarly encode information redundantly through quantum correlations, allowing information to be recovered from radiation even though any single bit of radiation seems to carry no information about what fell in. These connections between quantum information, entanglement, and gravity suggest that space-time geometry emerges from quantum entanglement patterns. The ER equals EPR conjecture, mentioned earlier, proposes that entangled particles are connected by Einstein-Rosen bridges, geometric wormholes. While these wormholes aren't traversable, they represent geometric connections corresponding to quantum correlations, suggesting space-time connectivity reflects quantum entanglement structure. Tensor networks provide models for how space-time might emerge from quantum information. In these models, quantum states with specific entanglement patterns correspond to geometries satisfying Einstein's equations. The entanglement structure determines geometric properties like distances and curvatures. This provides concrete realizations of emergent space-time ideas, though whether these toy models capture aspects of real quantum gravity remains uncertain. Quantum mechanics has also influenced other sciences beyond physics. Chemistry is fundamentally quantum mechanical, as chemical bonds and molecular properties arise from quantum behavior of electrons. Quantum chemistry calculations guide drug design, materials development, and understanding of biological processes. Computational quantum chemistry has become an essential tool across chemistry, biology, and materials science. Materials science increasingly relies on quantum mechanics to understand and design materials with specific properties. Quantum simulations predict material properties. The development of quantum mechanics represents one of humanity's greatest intellectual achievements. In less than 3 decades, from Planck's quantum hypothesis in 1900 to the mature quantum mechanics of the late 1920s, physicists revolutionized our understanding of reality. This rapid development required both brilliant theoretical insights and increasingly sophisticated experiments revealing phenomena that defied classical explanation. The history of quantum mechanics illustrates how science progresses through interaction between theory and experiment. Theoretical predictions like Bose-Einstein condensation, antimatter, and the Higgs boson were confirmed decades after their proposal. Unexpected experimental discoveries like the anomalous Zeeman effect and the Lamb shift drove theoretical developments. This interplay continues today, with theory guiding experimental searches while experiments reveal phenomena requiring new theoretical understanding. Quantum mechanics has also demonstrated science's international and collaborative nature. Scientists from many countries contributed to quantum mechanics development, often working together despite political tensions. The Solvay conferences brought together leading physicists to debate quantum mechanics foundations. This collaborative tradition continues in large experimental collaborations involving thousands of scientists from dozens of countries working on projects like the Large Hadron Collider and gravitational wave detectors. The technological impact of quantum mechanics has been transformative. Transistors, lasers, MRI, atomic clocks, GPS, LED lighting, solar cells, and countless other technologies rely on quantum mechanics. The quantum technologies currently under development, quantum computing, quantum communication, and quantum sensing, promise further transformations. Understanding quantum mechanics has become essential, not just for physicists, but for engineers, computer scientists, and technologists across disciplines. Education in quantum mechanics faces unique challenges. The theory's mathematical sophistication requires advanced background, while its conceptual strangeness contradicts everyday intuitions. Traditional physics education builds from classical mechanics and electromagnetism before introducing quantum mechanics. But some educators advocate earlier quantum exposure, arguing that students without deeply ingrained classical intuitions might find quantum concepts more natural. Online courses, interactive simulations, and improved visualization tools are making quantum mechanics more accessible to broader audiences. Public understanding of quantum mechanics remains limited despite its importance. Popular accounts often emphasize the theory's strangeness, superposition, entanglement, and uncertainty, without conveying the mathematical structure and predictive precision that make it successful science rather than mysticism. Quantum mechanics is sometimes invoked to support pseudoscientific claims about consciousness, healing, or paranormal phenomena. These misappropriations exploit quantum terminology while ignoring the theory's actual content and constraints. Improving quantum literacy matters as quantum technologies enter everyday life. People will increasingly encounter quantum encryption, quantum sensors, and eventually quantum computers. Understanding what these technologies can and cannot do, their advantages and limitations, requires basic quantum knowledge. Educators, scientists, and communicators face the challenge of conveying quantum mechanics' essential features without either oversimplifying to the point of distortion or overwhelming audiences with technical details. The quantum mechanics research community continues growing, with thousands of physicists, chemists, engineers, and computer scientists working on quantum topics. Research spans from fundamental questions about quantum mechanics, interpretation and extensions to practical engineering challenges in building quantum devices. The diversity of approaches and perspectives enriches the field, with insights from one area often proving valuable in seemingly unrelated contexts. Conferences and workshops bring quantum researchers together to share results, debate interpretations, and forge collaborations. The field's rapid progress means that staying current requires continuous engagement with new literature, techniques, and experimental results. The pace can be exhilarating but also challenging. As established results are refined or overturned, and new phenomena are discovered regularly. Funding for quantum research has increased dramatically in recent years. Governments recognize quantum technology's strategic importance for economic competitiveness and national security. The United States National Quantum Initiative, European Quantum Flagship, and similar programs in China, Japan, Canada, and other countries represent multi-billion-dollar investments over several years. This funding enables large-scale experiments, technology development, and workforce training that would be impossible otherwise. Private sector investment in quantum technologies has also surged. Technology companies, including IBM, Google, Microsoft, Amazon, and others have substantial quantum computing programs. Numerous startups focus on quantum hardware, software, algorithms, and applications. Venture capital flows into quantum technologies have reached billions of dollars. This private investment accelerates development but also raises questions about intellectual property, access, and the relationship between commercial and academic research. The balance between open science and proprietary development creates tensions in quantum technology. Academic researchers traditionally share results freely, enabling rapid progress through collaboration. Companies developing quantum technologies need to protect intellectual property and maintain competitive advantages. Finding appropriate balances, where fundamental research remains open while specific implementations are protected, will be important for healthy development of quantum fields. Quantum technologies raise ethical questions deserving consideration. Quantum computers might break current encryption, potentially exposing private communications and stored data. Who should have access to quantum computing capabilities? Should governments regulate quantum technology development or deployment? How do we ensure quantum technologies benefit society broadly rather than concentrating power in few hands? These questions parallel earlier debates about nuclear technology, biotechnology, and artificial intelligence, but with quantum-specific nuances. Workforce development for quantum industries requires new educational programs bridging physics, engineering, and computer science. Quantum engineers need understanding of quantum mechanics, fabrication techniques, cryogenics, electronics, programming, and algorithms. Universities are developing quantum engineering programs, but the field's rapid evolution means curricula must continually adapt. Industry partnerships help ensure educational programs teach relevant skills. Diversity in the quantum workforce matters both for equity and for scientific progress. Physics and engineering have historically lacked diversity in gender, race, and socioeconomic background. Quantum technologies' growth offers opportunities to build more inclusive scientific communities. Targeted programs encourage participation from underrepresented groups, though significant barriers remain. Creating welcoming environments where diverse perspectives are valued improves both recruitment and retention. The global nature of quantum research creates opportunities and challenges. International collaborations leverage different countries' strengths, but geopolitical tensions complicate cooperation. Export controls on quantum technologies might restrict scientific exchange. Balancing national interests with scientific openness will require careful navigation. History shows that while nations compete in technology development, science ultimately benefits from international cooperation and exchange. Looking toward quantum mechanics' future, several key questions stand out. Will we achieve large-scale fault-tolerant quantum computers? Can quantum technologies address important real-world problems in optimization, simulation, or machine learning? Will quantum networks enable global secure communication? Can quantum sensors probe dark matter, gravitational waves, or other elusive phenomena? These practical questions will be answered through continued research and development over coming decades. On the fundamental side, equally important questions await. Will we find evidence for physics beyond the standard model? Can we construct a consistent theory of quantum gravity? Will experiments reveal modifications to quantum mechanics at large scales or high energies? Can we resolve the measurement problem and determine which, if any, interpretation of quantum mechanics is correct? Will we understand how space-time and gravity emerge from quantum information? These profound questions might require breakthroughs comparable to quantum mechanics' original development. The interplay between fundamental research and applications will likely continue driving progress. Practical quantum devices require understanding, decoherence, noise, and control at deep levels, driving fundamental research into open quantum systems, many-body physics, and quantum information theory. Conversely, fundamental discoveries about entanglement, topology, or quantum phases might enable new technologies. This virtuous cycle between basic science and applications has characterized quantum mechanics throughout its history. Quantum mechanics has taught us that nature is stranger and more subtle than we imagined. The comfortable classical world of our everyday experience is an approximation, valid in limited regimes where quantum effects average out. At fundamental levels, reality is probabilistic, non-local, and counterintuitive. Objects exist in superposition until measured. Distant particles share correlations defying classical explanation. Measurement changes what is measured. These insights have revolutionized both physics and our broader understanding of reality. Yet quantum mechanics is not arbitrary mysticism, but precise mathematical physics, the most accurately tested theory in history. Its predictions have been verified to extraordinary precision. Its applications power technologies transforming society. Its framework has been extended to encompass all known particles and forces, except gravity. This combination of conceptual strangeness and empirical success makes quantum mechanics simultaneously puzzling and triumphant. The journey into quantum mechanics reveals not just physical laws, but something about the nature of scientific understanding itself. Science progresses not by confirming common sense, but by following evidence wherever it leads, even when it contradicts intuition. Quantum mechanics required abandoning cherished assumptions about determinism, locality, and objective reality. Future physics might require abandoning other assumptions we currently consider fundamental. Quantum mechanics also demonstrates the power of mathematics to describe nature. The theory's mathematical structure, Hilbert's spaces, operators, and symmetry groups, seems perfectly suited to capturing quantum phenomena. Whether mathematics is discovered or invented, whether the universe is fundamentally mathematical, are philosophical questions. But quantum mechanics makes clear that mathematical description of nature is extraordinarily powerful and perhaps indispensable. The social and collaborative nature of science is evident in quantum mechanics, history, and current practice. No individual discovered quantum mechanics. It emerged from contributions by dozens of physicists building on each other's work, arguing about interpretations, and gradually converging on a mathematical framework explaining diverse phenomena. This collaborative process, with its debates, false starts, and gradual refinement, characterizes science generally, but is especially visible in quantum mechanics development. Quantum mechanics reminds us that science is provisional and open to revision. While quantum mechanics is extraordinarily successful, it's almost certainly not the final word. It doesn't include gravity, might be an approximation of a deeper theory, and faces interpretational questions after a century of use. Future physics will likely extend or modify quantum mechanics in ways we can't currently anticipate. Scientific humility recognizes both the power of current knowledge and the certainty of its limitations. The beauty of quantum mechanics, both mathematical and conceptual, attracts many researchers to the field. The elegant structure of quantum theory, the surprising connections between seemingly unrelated phenomena, and the profound questions about reality all contribute to its intellectual appeal. Many physicists describe quantum mechanics as beautiful, finding aesthetic satisfaction in its mathematical framework and explanatory power. This beauty isn't mere decoration but seems connected to truth. Beautiful theories often prove empirically successful, while contrived or ugly theories often fail. Why nature should favor mathematical beauty is mysterious, but the historical pattern is striking. Quantum mechanics exemplifies this connection between beauty and truth. With its mathematically elegant structure corresponding to nature's actual behavior, quantum mechanics has expanded human knowledge in fundamental ways. We now understand matter at its most basic level, why atoms are stable, how chemical bonds form, why materials have their observed properties, and how stars generate energy. This understanding enables technologies from nuclear power to nanotechnology. It reveals connections between concepts that seemed unrelated. It poses new questions deeper than those it answered. The story of quantum mechanics is still being written. Each year brings new discoveries, new technologies, and new insights. The field remains vibrant and rapidly evolving, with young researchers making crucial contributions. The next decades will likely see practical quantum computers, extensive quantum networks, revolutionary quantum sensors, and perhaps fundamental discoveries about quantum gravity, dark matter, or modifications to quantum mechanics itself. For anyone seeking to understand our universe, quantum mechanics is essential. It governs atomic and subatomic behavior, underlies chemistry and materials science, describes quantum fields and fundamental particles, and connects to information, theory, thermodynamics, and possibly gravity and space-time. No educated person can claim to understand the physical world without grasping quantum mechanics' essential features. Even if the mathematics remains challenging, quantum mechanics invites us to question our assumptions about reality while maintaining rigorous empirical standards. It demonstrates that the universe is under no obligation to match our intuitions. that nature's ways are stranger than we imagined, but not unknowable. Through careful experimentation and mathematical reasoning, we can understand even the most counterintuitive phenomena. This combination of humility about our intuitions and confidence in scientific method characterizes quantum mechanics' approach to understanding nature. As we've journeyed through quantum mechanics, from Planck's first quantum hypothesis through modern quantum technologies and ongoing searches for quantum gravity, we've seen how a theory born from puzzling experimental results transformed our understanding of reality. Quantum mechanics is more than physics equations. It's a new way of thinking about nature, information, causality, and reality itself. Its influence extends beyond physics into chemistry, biology, computer science, philosophy, and technology. The quantum world, invisible to our senses and contradicting our classical intuitions, is nonetheless the world we inhabit. Every atom in our bodies, every photon reaching our eyes, every electron flowing through our neural circuits obeys quantum mechanics. We are quantum beings in a quantum universe, even though evolution equipped us with classical intuitions suited for navigating the macroscopic world. Understanding quantum mechanics means understanding ourselves and our place in nature more deeply.